All right, so that we should be starting soon. Hi, I'm Jeremy. I will be basically just going through a study guide through for IBM. Qiskit. Name the study guide. So I'll try and like see if I can answer these questions correctly, and then we'll go over the right answers afterwards, right? So it'll be kind of interesting. Should be fun way to spend a random Saturday. Um, Thanks for joining me. So, uh, hello quantum world. That's Jeremy. I'm gonna be doing my best to kick some butt in this, and I may not understand all the math, or I may not be able to explain all the math correctly, but I'll do my best. Feel free to correct me if you feel like I'm wrong anywhere. So first off, let's take a look here. Let's just answer these questions, go over them. This is the study guide. I was actually invited to take the test in January, so that'll be cool. And take it for free. I have no monies, but I do have a lot of knowledge, which is actually pretty valuable. So, when it comes to training, these are the requirements that IBM is kind of looking for this IBM Certified Associate Developer Quantum Computing using Qiskit, right? Now, I'm just using Qiskit just because basically it's pretty easy to use. They set up things like Quantum Lab, IBM Quantum Lab. You just create an account with them for free, and you can actually run circuits on actual quantum computers, which is pretty cool. So I've actually run a couple of programs on quantum computers already. I did a course with them, qubit by qubit, through, excuse me, through the summer. Uh, but let's see. So requirements, right? So this is where I'm going to focus. Perform operations on quantum circuits. That's about 47%. And then you want to get basically you want to study the major percentages, the biggest percentages that they have, and then you can focus on the rest of it later. So biggest percentages wise, 47% is pretty big, so need to learn how to construct multi-qubit quantum registers, measure quantum circuits in classical registers, use single qubit gates, use multiple qubit gates, use barrier operations, return the circuit depth, extend quantum circuits, return open chasm string for a circuit, right? The next big percentage of the test that you should focus on would be use classical and quantum registers. That much I don't really know, but we'll find out what that means. Use operators, that I can definitely do. Measure fidelity. That I think is like error correcting or how correct you are with your programming. So that I might have issues with that. But we'll see, right? Let's keep going. Return experiment results. Return and understand the histogram data of an experiment. So I can kind of already do that. Um, Return and understand the state vector of an experiment. That I do know how to do just because they covered it in qubit by qubit. Return and understand the unitary of an experiment. That I might have to look up. And feel free, like if you have any issues or questions, definitely check it out. There's a sample test here, a study guide there. Definitely download those and get ready for it. I recommend like 2 to 3 months of prep if you're going to be doing it full time. part-time. It just depends on, how fast you learn. I'm gonna probably spend a few hours doing this a day, and I'm gonna try and use a lot of like uh, learning optimization for people's brains on top of that. So I'll try and cover some of those things in another video, but for now, let's just get back to this. The next big percentage at almost 20% is draw a circuit, plot a histogram of data, plot a block multi-vector, plot a block vector, plot a Q-sphere, plot a density matrix, and plot a gate map with error rates. So I think I know how to do this one and this one, or those two. Yeah, those two. I don't know the rest, so I'll have to study some of those. And then access AER provider. So this is just basically uh, seeing if you know how to use a different backend, because these are different simulators. So the state vector simulator is kind of like a classical simulator, and then a QASM simulator is closer to an actual quantum computer because it'll bring noise into the mix. And yeah, I haven't really used this one yet, but we'll find out, right? So let's see what the study guide looks like. Study guide. I am drinking beer while doing this, so that's right. Okay, prepare for the Qiskit Developer Certification Exam. Here's some helpful resources, right? Okay. Defining executing visuals results of quantum circuits using Qiskit SDK. Understanding qubit gates and their rotations on the Bloch sphere. That's good. Understanding various multi-qubit gates and their effects on quantum circuits. Leveraging fundamental Qiskit SDK features commonly used in classes functions located in Qiskit circuit, Qiskit execute, providers, QASM, quantum information, tools, and visualization packages. Right? So these are pretty helpful links. If you're more of like a visual learner, try Composer, and then you can just like Lego it kind of style, like click and drag Lego quantum circuits that way. If you're more of like a developer, you'll want to use Lab. Um, if you like using code and things like that for this, Lab would be the way to go. Okay. So there's a bunch of tutorials here. Definitely check this out. Research it, or I mean, study it at your own time. Right now, I'm just gonna go over the sample test and see if we can get some of these answers correct. Uh, and if not, then you can see how to not get the wrong answer. Anyway, what statement? Start with number one. What statement will create a quantum circuit with 4 quantum qubits and 4 excuse me, and 4 classical qubits? So far, I don't think any of these really make sense. I think this one makes more sense. These upper two, right? Um, so if you're always and ever having any issues, definitely, try things out. So let's say QC equals quantum circuit, right? And then we'll plot it out for uh, and we'll do, I don't know, QC dot draw to visualize it. So that's what that does. So it looks like the answer is A. Just because this one would only return just the qubits, and we can test it out. You don't have to trust me on that. Let's try it. Okay, let's do that. And then let's rewrite it as QC equals quantum get just the number 4. So the rest of them don't make any sense. Oh, I forgot to draw it. QC dot draw. Maybe I'll separate them just because way they're in different lines. So not, and then you can compare them. There you go. So 1, 2, 3, 4 qubits, and then 4 classical bits, and then 1, 2, 3, 4 qubits. So that's the difference. So here it looks like the answer is A. All right, let's keep going. Given this code fragment, what is the probability that a measurement would result in sorry, I forgot how to read this. I know it's so it's the state of a qubit 0, I think. QC equal quantum circuit 1. Rotate ry 3 times math dot pi divided by 4 0. So what does the ry gate do? Let's find that out. QC equals quantum circuit. QC dot ry. Looks like we have to put something in there. Still won't work, huh? Okay. 3 times math 4 and 0. So it takes a lot of parameters. It looks like this is not working. Okay. Math is not defined. I think that's a Python library, isn't it? Let's see. That's probably why it's not working. Yeah, it's there. How do I import it? Just import math, probably. Visualize transition. All right. I probably spelled it wrong. Let's some review. Okay, where'd it go? Oh, it's just visualize transition. Silly me. Let's try that instead. Wow. So rude. Don't you copy things that I tell you to copy? Sometimes computers, sometimes you're such a jerk. Copy that. Oh no. Endless loop, huh? Can you just stop it? Oh, there we go. Okay, so let's see what this does. Starts at 0, and then it rotates to in between 1 and x. See that? That's what that code does. So let's see if this is 0. No, this is 0. This is 1. This is, I guess, 0.5. This would be like 0.4 probably. I'm gonna guess C. That's what it looks like to me. I don't know if it's an open book test or not, so I honestly wouldn't know how they expect you to know what 3 times math pi divided by 4 would be, but if they do, I apologize. If they don't, then it's good enough. But let's visualize this one more time. So this is a qubit, right? This is the start of the qubit at 0. So given this code fragment, what is the probability that a measurement would result in 0? It's very low, because so let's watch this loop one more time, right? So once it's done with the RY, like it's way closer to the 1 than it would be 0. So it's a lot. That's why I think it's C. So let's mark my answers with a J, just so that I know what I guessed, and then we can go over what the correct answers are. Right. So let's move on to the third problem. Assuming the fragment below which 3 code fragments would produce the circuit illustrated. I'm gonna take a swig of this. Hold on. Inspiration, right? So quantum register. See that I don't really know about quantum registers. So let's try and read some of this. Where For art thou quantum register? Had something up. It was okay. So this is in Qiskit Terra. Let's pull this up. Quantum register or quantum circuit, quantum register, classical register, right? Are the main objects for Qiskit Terra. You can create custom circuits, combine existing circuits, manipulate circuit structure, and index into circuit elements, right? Okay. It imports a bunch of stuff for you, and then this is how you create a quantum circuit. So Q0 quantum register. Sorry. So this is how you create a quantum register. 2, and then qubit 0, right? We can test this out here. Let's take a look at what this code does. And then what, like U0 dot raw. Oh, something is not working here. Let's go back and add some more. Basis name. What? Basis state. Huh. Maybe it's deprecated or something. That's one thing that when you're working with like bleeding edge technology, it kind of changes a lot, right? Here, let's just do import all and save. Wow, it does not like me. Invalid syntax. Yeah, silly me. Ah, has no draw attribute. Still doesn't feel right. D, declare the following. So it does. Name is optional, is not given. Qiskit QI is an integer, which will count from 0. The name and size can be returned using the following. You can test. Register. Does not want to save or something. Okay. Barbiton. didn't really learn quantum computing this way, so I feel like this is like a more basic way of creating registers or creating circuits. I don't really know the difference between a register and a circuit. I was just creating circuits from the get-go. Like this feels like it's overcomplicating too many things. Anyway, uh let's just check out what these do, I guess, you know. Two. Oh, and then compare. So for me, it looks like this is applying an H gate, applying an H gate, and applying an X gate on the ANC. So everything's breaking. Maybe someone's trying to hack me or something. Who knows? The BZs always want the information. I mean, it's publicly available, so I wouldn't understand why they would want to, but whatever. You know, stop doing that crap. This is getting annoying. Okay, let's just try shit stuff out. QH, and then, oh, okay, that makes sense. Um, I'm thinking, let's see, let's try. Draw. Let's try A first, I think. And then if A doesn't cut it, so NP quantum 2. Oh, stop it. By the gods, you're annoying. I always recommend writing these out just because it'll give you better practice. It'll stay in your head longer. Input ring not defined by the gods. This crap is so annoying. How is it not defined when I'm literally defining it right there? You're funny. Oh, looks like I misspelled it. Okay. So let's try A. QC.H. And then we're going to provide which reg we're doing, right? Let's see if that even works. It looks like it works, so that's a good sign. If it's running, then QC.X and qc.raw. So it does not look like A is the correct answer. Because we have, well, hold on. Yeah, let's try something more specific, right? Let's see if this does any change. It doesn't look right. Oh, whoops. Looks like it's just adding a bunch of them now. Uh, how do you reset variables? Let's just reset it all over now. Restart kernel. And then run these bad boys, eh? Oh, there you go. So it looks like the answer is B as in Bravo. Actually, hold up. Wait a minute. Of course, you'll have to restart the kernel again because these species. I don't know what's up with like computers always having some kind of errors and things like that. It's like, come on, yo, you gotta do me like this. Same answer, mate. So yeah, I believe it's B. Final answer B. That's with some intuition and some resetting kernels, right? Okay. Given an empty quantum circuit object QC with 3 qubits and the 3 classical qubits, or sorry, 3 classical bits, which one of these code fragments would create the circuit? Measure 0, measure 1, measure 2. So measure, okay, and then um so for me I think it's measure all. Uh, we'll test it out, but once you measure one, well, actually they're not they are separate, they're not interlinked, so they should give you different results each qubit. But let's test it out, right? So uh let's redefine QC equals quantum circuit. I didn't spell it. And we'll say what, 3? And QC dot measure and then draw. Silly. what it looked like. Okay. And let's compare that. So I'm thinking C, but it might be a little different. Let's try be classical measure. It even works this way. And then specific 0, 0. Bracket 0. That's a comma, and then a comma. Get 1, comma 1. Get measure takes 3 positional arguments, but 4 were given. What are you talking about? Positional arguments. Oh, got it. Let's try this one. 1, 2, 3. Silly me. 0, 1, 2. No, now do it. Yeah, that works. Let's try this one. Oh, looks like I was wrong. I have no idea why I'm wrong, but looks like the answer is. They look the same, almost the same, but this one matches this one perfectly, so I'm going to go with this answer. So it looks like A is correct, not C. And if you find out why I'm wrong, definitely, let me know, right in the comments. Explain it to me, yo, because I'm still learning. That's why I'm here. Which code fragment will produce a maximally entangled or Bell state? A maximally entangled Bell state. I'm thinking B. No, let's test it. Bell equals Qiskit dose. Right. And CX, which is a C naught gate. And then the C naught gate takes the input qubit, and then the qubit it'll control. And then we apply a gate. Oh, sorry, an H gate, then an X gate. So 2, 0, and then freaking misspelling. Um, I don't think that this is the right answer just because you need to have this X probably on the 0 to actually make a change on the H or have the H for that. So it is not B. All right, we tried B. It's not B. Um, I think we should try A next, maybe. Let's see. It could be C. So the next ones are A or C, right? Let's try A first. Copy all this and then just change the order. So let's try an H here. And then an Qiskit. And run that. That is not entangled. I mean, it is entangled, right? So they're both entangled, but this will make it 1. So this will be a 0. Could be a 0 or 1, right? Which, and then this entangles that, but this is always going to be 1. So that might actually work for entanglement. And then let's try and see what C looks like, but I'm thinking it's A. That's my guess from here, but let's try C again, and then we'll compare the two. That's weird. I'm gonna go with A. Um, I think that's all I'm gonna review for today. Just these 5 questions. I'll keep going later. Um, maybe tomorrow and do the rest of this. But we did 5 questions. It took me a bit. We got it. Let's end it there. I hope you enjoyed some study guide studying with Jeremy Ritamarita. And wherever you are, I hope you enjoy your life and happy days, See y'all later.